Hello people, in this video I'll talk about XGBoost, also known as extreme gradient boosting. It has emerged as a go-to algorithm for a wide range of data science tasks. These days it has gained immense popularity for its exceptional predictive accuracy and robustness, making it a favorite among the data scientists and machine learning enthusiasts like us. So, let's get ready to boost your knowledge and unlock the potential of XGBoost. XGBoost can be used in many applications such as regression, classification, ranking, recommendation system, image recognition, and many more. One of the popular example is MNIST and data classification. It can be used to predict digit of MNIST dataset. Disclaimer: XGBoost perform quite well only for structured or tabular data. If you are dealing with complex image or other data, you have to go for neural network or other robust algorithm. Now I will explain how does XGBoost perform regression with its unique tree. To make it easy, we will take a simple dataset. We will analyze how does amount of coffee will affect the quality of sleep through regression. Here, x-axis represent amount of coffee and y-axis represent quality of sleep. For the ease of calculation, we are only considering 4 data points. These 2 data points have positive value for the quality of sleep, so it indicate this observation of amount of coffee is helpful for the quality of sleep. As you can see in the screen, the lower 2 data points, these data points have negative value of the quality of sleep, so it indicate this level of coffee badly affect the quality of sleep. The very first step in fitting XGBoost tree to training data is to make initial prediction. Here we take 0.2 is a initial prediction. This value can be anything. You can pick 0.1, 0.5 and whatever value you like. The black horizontal line corresponds to initial prediction 0.2. The residuals are the difference between observed and predicted value. Residuals indicate how good or bad initial prediction is. In the screen, you can see the dotted red line between initial prediction 0.2 and observation. Now XGBoost fits a regression tree to the residual. We can call this tree a XGBoost tree. Now let's talk how to build a regression tree for a regression. Each tree start out as a single leaf and all the residual go to the leaf. Here we can see 4 different values in the first leaf: -12, 9, 13 and -4. So this is the first residual, second, third, fourth: -12, 9, 13 and -4. Now we need to calculate similarity score. Similarity score is sum of residuals square divided by number of residual plus lambda. Here lambda is regularization parameter. We will discuss about it later in detail. For this example, we will set lambda is equal to 0. Then we put all the residual here, minus 12, 9, 13, minus 4, and we take square divided by 4, number of residual plus lambda. And we got similarity score for residuals in the root is equal to 9. We call the first leaf root because it is the starting of our tree. Now the next step is to split the root leaf into child leaves by clustering similar residuals. To perform clustering, we require a specific threshold. So we select the first two observations with lowest amount. Here we pick 14 and 22, these two observations. We then determine the average of these two observations, which serves as a threshold for splitting. The average amount of the two lowest observation is 18, is visualized in the black vertical line. Consequently, we divide the observations into two groups based on whether their amounts are less than 18 or not. Observations amount less than 18 belong to the left leaf, so their corresponding residuals are assigned to the left leaf as well. Here, the residue of the left observation is 12, so we put it on left leaf. On the other hand, all the remaining residuals located to the right of the threshold line are assigned to the right leaf. Here we can see 9, 13 and minus 4. All these residuals are in right leaf. Now we proceed to calculate the similarity score for the left leaf. As there is only one residual on the left, so we square the value 12 and divided it by 1 plus lambda is equal to 0. This results in similarity score of 144 for the left leaf. Similarly, we compute the similarity score for the right leaf. Since there are 3 residuals on the right leaf, the similarity score is determined by squaring 9 plus 13 minus 4 and dividing the sum by 3 plus lambda is equal to 0. Finally, we annotate corresponding similarity score at the top of each leaf for notation purpose. Did our tree split the residuals correctly? Now let's dive into how our tree is clustering similar residuals. We can evaluate the effectiveness of the splitting by calculating the gain of each split. To find the gain of splitting, we add the similarity scores of the left and the right leaves and subtract the similarity score of the root leaf. By incorporating the similarity scores value into each leaf, we achieve a gain of 243 at the threshold level of 18. Similarly, we need to determine the split gain at other threshold levels. For the next threshold, we calculate it using next two observations, 22 and 36. The new threshold will be the average of these values, which give us 29 to split the root leaf. As we can see here, the black vertical line split the observation into half. Now we construct our new tree based on the new threshold. Residuals minus 12 and 9 are located on the left leaf as their observation values are less than 29, while values greater than 29 resides on the right leaf. We can see 13 and minus 4 are on right leaf. We proceed to calculate the similarity score for both leaves and determine the gain based on updated similarity score. Here we get gain of 36. Similarly, we continue this process of finding next threshold using the next two observations and calculating similarity score for the newly split leaves. And this is our final threshold because we didn't have any other observation behind this last observation. We calculate gain of each leaf. For the left leaf we got 33.33 and for the right leaf we got 16. Here we are also using lambda is equal to 0. Now then we compute the gain at threshold value at 42. We can see the gain is 40.33. Now we have a comparison of the gain at different threshold levels. It becomes evident that a threshold level below 18 provide better result for splitting observations. Here amount less than 80 have value of 243, which is greater than other values. So we can conclude that amount less than 18 is better for splitting observations. So we will use amount less than 18 as a threshold for the first branch. Since we have obtained highest gain at threshold level of 18, so we will use this value to split the residue in the first branch of the tree. Now, since there is only one residue in the left leaf, so we cannot further split it. However, we can split the right leaf because it contains 3 residual values. Let's consider a second branch. This branch is a root and calculate its similarity score. We got similarity score of 108. Next we need to split the branch 2. So let's take 29 is the threshold value. Note that we have already split the first observation from the first branch, so we are not considering it for second branch, so we are leaving the first observation. Here on the left leaf we have 9 because 9 is smaller than 29. It's on the left side, and on the right side of the threshold value we have 13 and -4. Now let's calculate the similarity score of both right and left leaves, and we got similarity score of 81 for left leaf and similarity score of 40.5 for right leaf. Now we calculate the gain of split in branch 2 with threshold value of 29. So we add similarity score of right and left and subtract with similarity score of root, and we got similarity score of 13.5 at threshold level 29. Now we are shifting the threshold level to 42 here, and then we are splitting the branch 2 again. Now we have residual 9 and 13 on the left side of the threshold level and -4 on the right side of threshold level. So we calculate similarity score for both left and right. Now calculating the gain in branch 2 is a threshold of 42. We get gain of 150. Now we have the gain table, and the largest gain value is at threshold level of 42, 150. Therefore we will use 42 to split the observations in branch 2. While we continue splitting the tree further, we have already gained how to split a tree using threshold values, so there is no need to compute the tree further. We can perform pruning on the XGBoost tree based on its gain value. The gain value is calculated for each branch. Here we have gain value for root is 143 and gain value for branch 2 is 150. To begin pruning, we consider the parameter gamma and calculate the difference between gain at each branch and gamma. If the difference between gain and gamma is less than 0, we proceed to prune the branch. Pruning starts from the lower branch of the tree, so we always move in upward direction. Let's assume the value of lambda to be 160. Now we will calculate the difference between gain value at each node and gamma. For the lower branch, the difference is negative value, so this branch will be removed. For the root, difference is positive value, so the root will not be removed. Now assuming gamma is equal to 300, we find the difference between gamma and gain to be negative for branch 2 and also negative for root, so both of the branch will be removed. Now again consider gamma to be 200. For the root, the difference is positive value, so root will not be pruned. For the second branch, the difference is negative value, so branch 2 will be removed. This portion will be removed. Lambda is regularization parameter, which is intended to reduce prediction sensitivity of each observation. For better understanding with an example, let's build a tree just like before, but using lambda is equal to 1 instead of 0. Then we calculate similarity score of the root using lambda is equal to 1. We get a score of 7.2 by putting lambda is equal to 1. Similarly, we calculate the similarity score of each leaf by putting lambda is equal to 1. Here we can see on the left leaf we got similarity score of 72, and on the right leaf we got similarity score of 81. Now let's compare the similarity score with lambda is equal to 0 and lambda is equal to 1. As we can see, for root with lambda is equal to 0, similarity score is 9, and with lambda is equal to 1, similarity score is 7.2. We can see significant drop in similarity score with lambda is equal to 1. Similarly, for right leaf, it dropped from 108 to 81. So we can conclude that with a larger value of lambda, similarity score decreases, and the quantity of decrease is inversely proportional to residual in each node, because when the number of residual increase, we will divide the sum of residual by number of residual, so the value will be decrease. Now calculate the gain with lambda is equal to 1. We will use similarity scores calculated at lambda is equal to 1. We get left similarity plus right similarity score and subtract it with similarity score of root, and we got gain of 145.8 at lambda is equal to 1, and we have gain of 243 at lambda is equal to 0. So gain with lambda is equal to 0 is way more larger than lambda is equal to 1. Now again, let's prune the tree with the updated value of gain with lambda is equal to 1. Let's assume the value of gamma to be 160. Now we will subtract gamma from gain, so the value will be negative number, so we will remove the branch. We can see by choosing a positive value of lambda, our branch can be removed. So lambda plays a significant role in pruning tree. Even though setting lambda is equal to 1 doesn't always result in pruning trees. So by doing so, it prevents from overfitting the training data. So we call this is a regularization parameter. Now let's determine the output of leaves regardless of lambda and gamma. The output equation for the output of leaf is almost the same is similarity score, except we don't square the sum of residuals here. For this leaf on the left side, we put the value of residual and divide by number of residual plus lambda, and we got our value minus 12 for left leaf. We write output leaf value just under the leaf. For notation, we write output is equal to minus 12. Now we find the output value of left leaf of branch 2. Here there are two residuals, so we add them, 9 plus 12 and divided by number of residuals plus lambda, so 22 divided by 2 plus 0, so we got 11 for left leaf of branch 2. We write output here for notation. Finally, we calculate output value for right leaf of branch 2. We put minus 4, which is residual, and divided by number of residual, which is 1. So we got minus 4 is the output for right leaf. So with this newly built tree, we can make new prediction. XGBoost generates new predictions by utilizing an initial prediction with the chosen value being 0.2. We will start generating new prediction. To obtain a new prediction, we combine the initial prediction with the output of XGBoost tree, which is multiplied by the learning rate. By default, the learning rate is set to 0.3. For an example, when considering an observation with an amount 14, as we can see in the screen, the highlighted purple dot, it's with amount 14. We calculate a new predicted value by adding the initial prediction to the learning rate multiplied by output of tree. In this case, the initial prediction is 0.2, 0.3 is learning rate, and minus 12 is output of the tree. When you pass 14, then it will generate minus 12, and then we get result minus 3.4. The new predicted value demonstrate improved proximity to the observed value, resulting in smaller residual compared to previous residual. Thus, we have taken a small step in right direction. From observation, we can see the new residual, which is dotted green line, is smaller than vertical dotted red line. Similarly, for another observation with an amount 22, we derive new prediction using initial prediction. In this case, new prediction is 3.5. In the diagram, we can see the new residual vertical dotted green line is smaller than previous residual. So residual is smaller than before, so small step is taken in right direction. Moving on the observation with amount of 36, we once again obtain a new prediction by combining the initial prediction with the output of the tree multiplied by the learning rate. Again, we got 3.5. By plotting the new residue, we can see the residue is smaller than previous, so we are also moving in right direction. So finally, let's calculate the new prediction value for the observation with amount 48. We got output from tree -4, because when we give 48 to the tree, it will first go to the second branch, and second branch will give output of -4. So we put -4 here, and we got new prediction -1. So when plotting new residue, we can see it is smaller than before, so we are in right direction. Is new prediction is closer to the observation. With updated residuals, we continues constructing new trees with until the residue become significantly small, or we reach the specified iteration. This iteration process enhances the predictive power of XGBoost. To summarize the process of building an XGBoost tree for regression, we follow these steps. Firstly, we establish the initial prediction, which we have set to 0.2 for our example. Next, we calculate the similarity score for the root node, and subsequently calculate the similarity score for each leaf after the splitting process. Then we determine the gain of each split. We focus on threshold values where the gain is higher, and construct the XGBoost tree by creating branches through splitting. We have also explored the concept of pruning the tree and gain an understanding of how lambda influence the pruning of XGBoost tree. Lastly, we grasped the method of updating the XGBoost tree based on initial prediction. This involves incorporating the learning rate and the output of previous XGBoost tree. By following these steps, we can effectively construct and update an XGBoost tree for regression tasks, enhancing the accuracy of our prediction. Thank you very much for watching this video.